Hi, I'm Mark Hochman from PCWorld. I'm here with Mike Housholder of xMEMS. So again, we're talking about MEMS technology. And for those of you who aren't familiar with what MEMS is, Mike, would you just give us what MEMS stands for as an acronym and then tell us why it's cool?
Sure. Yeah, so we're a fabulous semiconductor company. We build chips. MEMS is a type of semiconductor technology, stands for micro electrical mechanical systems. So we put microscopic moving structures inside of silicon, inside of chips.
So why is this sort of novel and interesting as opposed to just, pushing electrons through a wire?
Yeah, and so MEMS has been around for decades, but in terms of consumer electronics, it started to pick up in the mid-2010s. It's in pretty much every electronics device that you carry today. You've got MEMS motion sensors in your phones. You've got MEMS microphones, phone, car, everywhere. Pressure sensors, they're all over the place. They're already out there in devices. We're basically doing a new type of MEMS device, more piezo MEMS technology. So we have a thin film piezo layer in the silicon that's actually physically moving the silicon up and down so we can move air and create stimulus.
And that, of course, sounds like a loudspeaker, which is sort of what you guys have done. Is that right?
Yep. So for the past several years, we've kind of made our name in a new type of speaker. The speaker has been unchanged for a century. Coil, magnet, paper, plastic diaphragm. We've moved it all into a silicon chip. So we have these MEMS structures inside the chip that move up and down. They move air to generate sound. So we're just now getting our speaker products to market. You can see a few products here from Creative Labs, SoundPeats, many more coming down the path, but that's really how we got our name. And now we're announcing something different.
Yeah, so let's talk a little bit about that. So what's the, how does that transition work from pushing air for generating sound into pushing air towards cooling a chip?
Exactly, so it's a progression. So our first speaker chips, even though they're MEMS and silicon, they worked on the same transduction principle to produce sound. They pushed air to generate sound. But in November 2023, we announced a even new type of speaker, basically our second gen speaker called Cypress. And that changed the way sound was generated. Instead of pushing air, it was really sound from ultrasound. So we built this ultrasonic transducer that was creating these air pulses at ultrasonic frequencies that would then change the pressure in the ear to create audible sound. So that was our first ultrasonic transducer, and we knew that if we could get it to work for sound, a couple little tweaks here and there, and we could get it retuned to basically generate airflow for cooling.
Okay, so this chip is called what?
This is our µCooling chip. So we have our first part number, which is less important, but XMC-2400.
Okay, so at least we know what we're talking about.
But it's part of our µCooling line of cooling devices.
Okay, so again, just because some of you are familiar with FROR, some of you aren't, tell us a little bit how it works.
Yeah, so again, we've got this thin film piezo layer in the silicon.
Okay.
So it's operating, basically moving silicon up and down at ultrasonic frequencies.
Okay.
That is generating air pressure inside the chamber of the chip. And then we have a valve structure in the chip. So once we're generating pressure inside the chip cavity, once that pressure reaches a certain level, a valve opens to release that pressure, which creates airflow.
And how many times per second are we talking about in terms of?
Yeah, this is hundreds of kilohertz.
Hundreds of kilohertz.
Yes.
Okay, great. And so it's mounted to the top of a silicon chip as a sort of replacement for a passive cooler?
Exactly.
Right.
So again, it may not show up well on camera, but this is basically our µCooling chip.
Right.
So it's about 9.5 by 7.5. And really cool, it's 1mm thin, and that's really going to play a key role in the markets we go into and where we deliver cooling.
Right, and that's where there's a little differentiation right now between you guys and FROR. You guys are playing into the smartphone market, is that right?
Exactly. I think we'll play into multiple markets, but I think the smartphone is the most interesting one, and FROR is clearly a pioneer in this space. They've got product out on the market in the PC market. we thought that our size and our thinness was perfectly suited for pretty much the largest market out there, which is smartphones, but also they're one of the thinnest devices, and that's where our thinness will come into play. Phones, for the most part, don't have fans today.
Nope.
You can't accommodate a 3mm fan. You really need, all the semiconductor components in phones are basically a millimeter or thinner.
Right.
So we've got the perfect cooling solution for that.
Now, I asked about this earlier, but I'll ask about it again. So gaming phones, yay or nay?
Sure. Pretty much any phone.
Okay.
Whether it's flagship, gaming, they all have a heat dissipation problem.
Mm-hmm. And now, obviously, Frohr is sort of attacking laptops. You guys are attacking smartphones. You guys think that you could be direct competitors at some point?
I'm sure we're going to come across each other in the market, but this is a huge market.
Sure.
And in big markets, there's never just one player. So I think we have different takes on the right solution. And we think we're a perfect fit for certain markets. They may be an ideal fit for other markets, but again, I think there's room for competition.
So draw some comparisons between you guys and Frohr, because one thing I did appreciate was you sort of addressed differences in both size and airflow and so forth. I think you guys are sort of trying to basically say that you're winning on efficiency. Is that correct?
Yeah, I think in terms of our silicon, we're a fraction of the size of Frohr. Mm-hmm. Looking at their solution versus ours, they do generate more airflow, but they're also significantly larger.
Sure.
So if you just compare airflow per package size volume, mm-hmm. we're about 15x more efficient than they are.
And how many are we talking about? One essentially valve per chip, or are we talking about an array of valves? Is that the right terminology to use, by the way?
If we just look at it as a chip, mm-hmm. It will scale to the needs of the application.
Okay.
So in an ideal world, something like a smartphone, we can probably get away with one chip. Mm-hmm. As you scale up into bigger devices, AR, VR goggles, laptop PCs, you're probably going to array them to get the desired airflow.
But in one chip, is there one valve, inlet valve with the
No,
air?
So this current chip, it's basically a 2x4 array of cells. So we basically have a cell architecture mm-hmm. that is basically an airflow and valve combination. We array them in a 2x4 array for this first chip. Mm-hmm. But again, that's what makes the technology scalable. We can scale down the number of cells, scale up the number of cells to fit the desired application. And once we've maybe reached the limits of how big we want the chip to be, then we can just array these thin, tiny chips to hit the target.
And how much airflow does the chip itself put out?
Yeah, so this first chip, mm-hmm. the XMC-2400, it'll generate about 39 cc per second of airflow and about 1,000 pa of back pressure.
Okay. And so what does that translate to into removing heat? We've talked about watts of heat before, which isn't a great necessarily terminology, but give us some sort of sense.
Yeah, and that's also system specific, and those proof of concepts are underway at the moment. Okay. So whether it's smartphone or other applications, we're integrating that into the device and basically doing before and after measurements to kind of quantify how much more power can this device draw and still operate at its max potential.
And you're in production right now or pre-production?
This is all pre-production. So this is the initial technology announcement for the product. We'll be engaging our alpha customers as part of this announcement, and that will begin the progression towards a production release.
And then where are you fabbing this?
So we're dual sourced today. Mm-hmm. Again, with the demand we see for our speaker products and the demand we're anticipating for this interesting µCooling technology, we now have two fab sources. Our first and primary fab is TSMC today. Mm-hmm. They've been a longtime partner of ours through several MEMS companies. And now we're fortunate to also have Bosch on board. And Bosch is, again, one of the top three fabs. I think they may be the number one MEMS fab in the world. So we've got the largest pure play fab in the world and the largest MEMS fab in the world working with us on these devices.
Now, when we think about fabs, we talk a lot about in the silicon space, TSMC, for example, you've got, microns, nanometers, and so forth. How do you characterize a MEMS fab? And then, where the process technology is?
MEMS is its own beast. Sure. We're not down to 3 nanometer like the big CPUs and GPUs today. MEMS typically runs on legacy 8-inch wafer fabs. So all, it's deprecated equipment. It's very mature. So we run off of 8-inch MEMS processes. You don't really put a process geometry to it per se. So again, it's a different beast, but it's all 8-inch fabs.
Okay. Now, one of the things we talked about earlier was something that was actually, I think, fairly intriguing to me, was the fact that you guys think that there's a potential future where you guys not only are attaching this to the outside of a chip, but as inside of the chip, working directly with a silicon manufacturer. Talk a little bit about that.
Certainly, there's a lot of potential there. There's a lot of unknowns there.
Okay.
This really hasn't been done before, but because we are a all silicon implementation, and you start to look at what's going on in semiconductor packaging at the moment with chiplets and tiles and 2.5D, 3D packaging, can you bring the notion of a cooling chiplet into a multi-die package? So again, that's never been done before, and there's many unknowns and many challenges to overcome. But once you've got an all silicon implementation, the possibility is there.
Right. So hypothetically, and I'm only emphasizing this from a hypothetical standpoint, I mean, you could take a CPU tile and an I/O tile and a graphics tile, then put that attached to an xMEMS chip tile, where you'd have essentially an in-package cooling solution. Right.
That's the dream.
That's the hope. Right.
That's the dream.
Okay. And obviously, if we had something like that, you would need to work with whatever company was packaging that, which in this case, I guess, could be whoever, with vents in that package as well, because you'd have vents in your package and vents in that package to get air back and forth. Is that
yes.
right? Okay.
Yes.
Excellent. And what's the advantage of doing that inside of the SoC package versus the outside package? Is it more efficient?
Well, again, and one may not replace the other. It's really bringing all of your tool belt to the game, so to speak. Obviously, external cooling for really big CPUs, GPUs, unlikely to go away.
No, that's true.
But if you can bring cooling more locally to contribute to better efficiency, then why not deploy it? So, to be determined.
Sure, no, absolutely. Speaking of products, one thing that I did want to mention that we didn't touch upon previously, you guys are looking at smartphones, but you're also looking at SSDs. Is that right?
Yeah. So I think any device that fits into that thin mobile profile. So smartphones, tablets are obvious. External SSDs, wireless chargers.
Okay.
Anything thin and mobile where putting a 3 mm or thicker fan is an inconvenience or an impossibility.
Right.
That's right up our alley.
Okay, that makes sense. So where do we go? I mean, again, in the silicon space, we're sort of familiar with increasing clock speeds, shrinking line widths, additional cores, additional tiles. What's the progression in terms of MEMS cooling? How do you go forward?
Yeah, I mean, I think first and foremost is finding the right place for the chips as we're launching them today.
Yeah, you gotta sell it first.
We know how to package that. Right. We know how to build it. We know how to sell it.
Right.
And finding the right markets for that. As with our speaker technology, we'll have a roadmap. We'll have bigger chips, smaller chips, but also the core cell technology evolves over time as well. We're on 3 generations of our speaker cell technology, so greater efficiency with less silicon, better performance, less silicon. So we see the same progression with our cooling chips as well. The efficiency, the airflow, the back pressure will improve over time, so we'll do more with less silicon. And then how that gets packaged, how that gets integrated into a mobile system, that will evolve over time.
Makes sense. So I think that was pretty much the questions that I wanted to ask you. Any points or issues that I didn't touch upon that you wanted to mention?
No, I think you covered it all. And we do have a demo that will hopefully get filmed a little bit later.
Yes, actually, you know what? Let's go ahead and let's talk about a little bit about that right now. So, what exactly are you have here? Is this sort of a proof of concept?
Yeah, so this is an early proof of concept showing that a small semiconductor chip can now generate airflow. So this is kind of a crude demo, but a very functional demo. So we basically have our cooling chip implemented in this 3D printed structure back here. So we've got the chip implemented in back. We've got basically power, ground, and control signal through this USB-C cable going into a control box. So the chip is connected to a manifold, which is connected to basically a passive propeller. So once I turn this on, if the chip is generating airflow, it should be able to blow this propeller.
Right, and that control box obviously is just a control box for right now. It's not something you need for a
Correct.
product implementation.
This won't fit in a phone.
No,
but
it will not.
so we do roll our own control ASICs. So these are our speaker chips, by the way, and all of our speaker chips have a companion drive ASIC that's a fraction of the size of the MEMS chip. But these control ASICs basically control the MEMS. And we've already rolled our control ASIC for our µCooling technology. It's in our labs being brought up at the moment. So until such time, I got this big box. But this box shrinks into this chip.
Okay, you want to fire it up?
Let's so basically what the other cool characteristic of this chip is airflow can be bidirectional.
Sure.
So I'll actually show the demo in 2 stages. I'll show airflow going forward, so it's basically a blower. I'll stop the propeller, and then I'll turn on reverse mode, and we're basically creating more of a vacuum, and you'll see the propeller basically spin the opposite direction. So you can place the chip at the source of the heat and blow the heat away from the heat source. You can also place a chip maybe at an ambient vent where you want to suck heat out of a system.
Sure.
So we've got that flexibility with the technology.
Okay.
So let me fire it up. And once this powers up, you'll start to see the forward airflow first.
Okay. All right.
And there we go.
Excellent. And we'll go the opposite way.
And I'll shut it down. You'll see the propeller stop, and then I will switch it up.
All right.
And pay close attention. The propeller will switch the other way. But that is a semiconductor chip generating airflow, 1mm thin.
That's great. So again, with the whole heat aspect of it, you're using it to essentially double up. I mean, you're talking about pulling in ambient air from the outside world and then pushing the hot air from the chip to someplace else, which could be out of vent too.
So yes, I mean, you're not only spreading heat, but you're expelling heat.
Fair enough. Okay, cool. Yeah, it's a fascinating technology. I mean, we're right on sort of the early days of seeing what this could be used for. I mean, we're talking about, products that could be revised and evolved over successive generations into multiple different products. So, I mean, conceivably, you could conceivably replace maybe a passive heatsink at some point in time with sort of an active but still very low profile cooling chip.
Yep. So. But yeah, the concept of now active cooling in a smartphone is hopefully going to meet the needs of these AI connected devices in the future.
Okay. So, Mike, thanks for your time. We'll have the story on PCWorld.com, but please stay tuned to PCWorld's YouTube channel for more interviews like this, more features, more podcasts, the whole works. Thanks for watching.
Thanks, Mark.
Mm-hmm.